Hello and welcome to this tutorial about some new tools we have developed in Lead-DBS, which are the Sweetspot Explorer, the Network Mapping Explorer, and the Fiber Filtering Explorer. They all work in a similar way, but one, as the name says, is for mapping sweet spots. The other one is for finding network maps of optimal connectivity profiles. And then the third one is for finding, which tracts are associated with a given variable. Now, I will base this tutorial on a group dataset that we made openly available. It's just the electrode localizations and UPDRS improvements. That is based on the paper by Svenja Troy et al. And in that paper you will find an OSF link where you can basically just download this lead group analysis mat file. So that is the link osfio/kj456. So once you have downloaded that file, simply go into MATLAB and open up lead group. Now all you need to do is to drag and drop that folder which contains the MATLAB file, drag and drop that folder onto the lead group analysis, and then you will see the contents of that. Now the three tools I'm going to show you are based either on a lead group analysis or on custom code, and you will find an example file if you prefer that in the Lead-DBS folder under support scripts, and then under sweet spot mapping, fiber filtering, network mapping example. Let's open up that one. Right, so in that file, which is again an example file, you can manually define, for example, in this case, 6 Nifty files. These could be VTAs, but in theory could also be brain lesions, MS lesions, any other things that in your mind make sense to do this analysis on. Then you also define one variable, for example, improvement of a clinical variable for these, it's seven clinical files. So for example, if you have paths to 7 Nifty files here, you would also have 7 improvement values. Then you could also define covariates. You don't have to, right? So these you could just delete in theory, and then also delete these. And then you would just have one variable and no covariates. Then you will just give it a name and you save that as something that mocks a lead group analysis file somehow. Right, we define the mocking of that here, so it's not a real lead group variable, we define that, but it's something custom for us. And then the three tools we're going to look at will open up just pointing to the file you just saved. Right, so the Sweetspot Explorer is that function, then there's the Network Mapping Explorer, and then there's the Fiber Filtering Explorer, that's this one. Right, but we'll start from lead group. So all we're going to do is basically, look at this file. We will, for now, just take the default distal nano or minimal atlas, and then we will basically just click visualize, and that will open up the 3D viewer Elvis, which will show the electrodes. Now you will notice some colors here. These are groups that Svenja put in. If you're unsure, just have a look at that paper where we explain a lot of things that you can do with lead group alone. These three tools I'm going to show you are pretty new, so at this stage, so they are not mentioned in the paper in detail. Okay, so few things you can do here. These are the electrodes of each single patient. You can select and deselect these. You can, of course, rotate the view and so on. And you could also say you want to save the current view as the default, and then if you ever want to go back to that default, you can do that by display current default view. Now the three tools I'm going to show you, and we'll start with the Sweetspot Explorer, are here. So this one with the plus and these two bubbles for an optimal and a negative sour spot is the Add Sweetspot Analysis Explorer. Then this will be the Fiber Filtering Explorer, and then this will be the DBS Network Mapping Explorer. Now before you are able to open the Sweetspot Explorer, you will need to calculate the VTAs, which are not included in this dataset, right? So to do that, you go back to the lead group window, and the stimulation parameters are already set here. All you need to do is to click on Calculate Stats and VTA. Make sure that there's no connectivity metric chosen here. If not, it would take much longer. Right, so let's click that, and then you will see that the data is being generated, and it will basically start processing with the first patient. That will take a while, but it will generate both the E fields and the VTAs. Now after that is done, you can go back to the 3D electrode view and click on the Add Sweetspot Analysis button. It will take another time to calculate that I've now skipped, where the VTAs are formatted in the right way. And as you can see after that, there will be a new button, which is your existing analysis, which gets a canonical name, which is based on the current date, and this one, in this case, it's even an old one. So this window will pop up, and maybe at this point it makes sense to disable the electrodes, and we can do that by disabling the groups, which will... Right. Now, you can see that in this case, the Sweetspot Explorer has already created a sweet spot, and that is because the auto refresh in my case was already on. So this is a crucial steering thing for all of the three tools. Works the same way in all of them, and maybe in the beginning it makes sense to not make to deselect that one. What it does is that as soon as I change something, it will automatically refresh the view. But maybe in the beginning we don't want that. We want to have control, and we want to be able to click the refresh view button. Maybe let's start here. You can see that there are positive voxels that can be shown and negative ones, and then we have 4 color buttons. Currently we are only showing the positive side, and unfortunately the sweet spot has the same color as the SDN does, so maybe that doesn't make too much sense. So maybe let's make it red, so just so we can see it. And then you also see the bottom color here, which is the lower part of the positives. So maybe let's make that white for now. And what you can see here now is that we see some blob that has peaks and that has valleys, and we only see the positive voxels and we don't see the negative voxels. Now, sweet spot mapping is indeed much more complicated than one would think when approaching the matter, and we really have to understand what is happening under the hood before we draw any meaningful conclusions here. And the reason for that is that the VTAs don't necessarily overlap all the time. So we have voxels that could be covered by 10 VTAs, but we also have voxels that are covered by 20 of them. Now, one of the best resources I can recommend is in fact all the literature, or most of the literature of Till Dembeck, who in my view has thought about these topics the most. And in particular, there's a current preprint, I'm sure it's gonna be published soon, which really looks at current approaches and reviews how things have been done in the past. Just to show you one figure, this is one which highlights different approaches that have been used in the past in the literature. Until has helped us greatly in trying to put these approaches or the general ideas of these approaches into this tool. So there's a lot that can be said here, and we'll go through each part of that in a second. But these presets might help you to get a specific idea. However, it should be said that these approaches, and there will be a warning window in the beginning of the tool, these approaches, parts of them have used very different parts, so only the main ideas are captured here. For instance, the Batson 2011 and Chung 2011 paper, they used very different VTA models than we use in Lead-DBS. Then the Eisenstein paper in Annals 2014 used no VTA model at all. Then, for example, the paper by Martin Reich in Brain 2019, after that used a different VTA model, but after that also used a clustering method. And then the Dembeck paper and the Elias papers, both of them basically used permutation statistics afterwards as well, right? So what we're capturing here is just the very rough and main idea, and we then have a cross-validation and prediction part of the tool that can be used to draw inferences based on the models we find. Okay, but now let's go through all of the tools we have. So first of all, we have to decide, do we want to base our analysis on volumes of tissue activated or on E fields, electric fields? So in Lead-DBS, VTAs currently are simply thresholded E fields. And they will be thresholded at a certain value that you can define here. A common value that we've used a lot in the past is 0.2 volts per millimeter. So basically the E field magnitude vector will be thresholded at that value to create VTAs. So as you can already imagine, the underlying data here is really E fields. So we have a probabilistic mapping of E fields in the STN in this case. And then let's assume VTAs for a minute. Now, if we select VTAs, we have to define how many VTAs need to be covering a certain voxel to be considered. And the reason for that is you can imagine some voxels in the fringe, in the periphery of the field, that are only covered by a single VTA or two VTAs, right? And maybe by mistake, this VTA is an outlier that has a very strong improvement, but it's not really true. So we cannot really draw statistical significance in that region. But if we would consider it, it would still have a larger value. Now we have to define basically, how many VTAs need to cover a certain voxel to be considered. We probably shouldn't set this to 0. We could in theory, right? But let's assume, so in this case, I think we have 51 patients. So if we would put it to 100, it would mean that we only consider voxels that are covered by all of our VTAs, which is also nonsense, right? So that wouldn't make too much sense. Then we would only consider the voxels really covered by every single region. If we set this to E fields again, the same thing applies. So again, the thresholding is not really taking place here anymore, but we still have, we still can define that voxels need to be or should be reached by at least, in this case, 10 or 20% of thresholded E fields, right? So the same area will be covered no matter if we take VTAs or E fields. So in this case, we could even say, we don't want to threshold this at all, because for E fields, every voxel will be covered by some part of the E field, because it's a continuous function that decays from the center of the electrode very rapidly. So in this case, such a setting could even make sense. But you are the researcher. You have to think about what is good for your analysis, what your hypotheses are. So, as in all these tools, unfortunately, we cannot really tell you what the best setting is. That we enter these sliders if we are unsure what is best ourselves. Okay, let's go back to VTAs here. Let's say at least 20%. In this case, 10 VTAs should fill a certain voxel to be considered. We only have one improvement value, a variable. That is the same variable as in our lead group analysis, so that's just taken over. If you should change things here, there is a tool to refresh the information from that to the Sweetspot Explorer. You can also change the name of your analysis. Let's say my analysis, and you will then see in our folder, the triad alp pre-processed, there will be a folder called Sweetspots, and in that there will be a file called myanalysis.sweetspot. Of note, that is simply a mat file in disguise, so you could load that with MATLAB just with the load command. The reason why we add such an appendix here is, first of all, to make it easier for users to know what files they are. The second thing is you can drag that to a Lead-DBS viewer and it will open up this file, right? So you could send this analysis to your colleague, and then that person could open it by just dragging it to a Lead-DBS viewer. Okay, so the second entry is whether we want to normalize this variable. And there are two options. One is the simple z-scoring, and the other one is a normalization, a Gaussianization based on a method by Sascha van Albada in 2017, which is I think, genius method to transform any random variable to a Gaussian variable. If you use that, look at the paper, right? So that is, not something one should add in carelessly. But let's assume, we have Parkinsonian patients and all of them cluster at something like a 70 to 80% improvement. So all of them are positive. Maybe 2 of them only are negative or something like that. Then it might make sense, depending on what we do later, to z-score them, to zero center them, to say, we want to have the average at 0 and then have, some positive values and some negative values. So it might make sense. It's not always the case. You can then say to clean the variable of interest from covariates, and that could be, for example, group or cohort regressors. So for example, if your analysis has different cohorts from different centers, which is not the case here. We have used the groups for different like for responders, the top responders. But let's assume we have data sets from 2 or 3 centers here. Then it might make sense to clean the variable from a group or cohort regressor that's automatically calculated. You could also clean it from the stimulation amplitude, and you could clean it from the VTA volume. Okay, next is the statistical test we use, right? Again, this is the presets that will fill some of your of these variables for you. But an important part would be, whether which test we want to use. Mean image would just mean, we average the scores of the VTAs. So we tag each VTA with a different value, with the improvement value. Let's say one VTA will get 80% improvement, the second one 20%, and so on. And then we average the voxels across, we average each voxel by the VTAs that cover that specific voxel. The N image is something different that's even less interesting. It's just, how many VTAs fill a certain voxel. So that will always have a peak in the center of your cloud of the VTAs. Right? This has been used, for example, by the Chung 2011 method, because all of these patients improved really well. So they just wanted to know, where is the peak? Where did all of these top responders, where were all of them stimulated? More interesting, I would say, is a t-test or then Wilcoxon test. Again, I can only advise you to read up the literature by Till Dembeck, especially the preprint I've just shown you, to get more information of, advantages and disadvantages. But for now, maybe let's use the t-test. And now the question is, against what do we test, right? So we have z-scored our variables now, so they are zero-centered. So in this case, maybe it makes sense to test against 0. We want to show voxels that are, significantly higher than 0 or significantly lower than 0. So this is a good method. The same would apply if we center it with the Van Albada method. But, if we don't correct the scores and the improvement, all of them are positive, and then we test against 0, that doesn't make too much sense. Again, it depends on what we want to do. We could then use that for cross-validation or so. Then it might even make sense. But, these are the details that you should really try to understand as best as you can to find a good method that suits your data. Let's assume we would have an improvement variable or a behavioral variable where half of the patients get better and half of the patients get worse, then that variable is already more or less zero-centered. Then testing against 0 could make sense. A different strategy could be to test against the average, right? So let's assume we don't zero-center the improvement variable. Then we want to test against the average improvement of these patients. If we go into that here, and we can look at the variable here. So, and then you see that, most of them get better. There are just a few with a negative sign. So the average value will be something positive. And then you're testing with the t-test against, the average improvement. So that is, in this case, already better than testing against 0. Alternatively, you could also test against the custom threshold. And there are more details that you could set. Again, read up the Dembeck paper about the details on that. Finally, you could correct the improvement variable against a certain regressors such as amplitude or VTA size. That is pretty similar to cleaning the variable above here, but a slightly different strategy. Now down here, and that is again something common to all of the 3 tools, you can select which patients go into your analysis, right? And the idea usually here would be to use a training and cross-validation set. Let's assume these first patients. And then we train our model based on that, and we keep that fixed all the time. We can then use cross-validations, and then finally in the end do the test on our holdout set, right? So this latter part of the data set could be our holdout set that we don't touch until the very end. So the idea of all of these tools is basically composed in such a way that you use the cross-validation prediction set for model comparison in the very beginning based on the test and training and cross-validation set, so the patients I just selected here. And then once you feel confident that your model is the final one, that you won't change anymore, then you test it on the holdout test set. So now one thing we can do as well is to select our training and cross-validation cohort. Let's assume we want to, build the first model on 27. Let's take some more. Let's take, 40 of the patients, and then we would have a test set, a holdout set that we don't touch currently, right? So we can select those, and then we can say create a subcohort from the selection. Now we want to call that maybe training and cross-validation. And then we want to use the rest of the patients, so the inverse selection, as a test set. So here you can see training CV, but now we want to create a subcohort from the inverse selection. And let me call that test. So now we have two sets, a training, cross-validation, and then a test set. So, and we will stay with our training and CV set throughout a long time to create hopefully a model that will then be used only in the very end to predict outcomes in the test set. Okay, so let's dive into the actual work. I have used pretty simple concept, right? I used Z-scoring of the improvement, so that means it's zero-centered and at least not Gaussian distributed automatically, but Z-scored. I test with the t-test against 0, and I don't correct for anything. Now, what it currently shows me is every t value, and so it's not, only showing significant voxels. What we can see here is that, these are the atlas structures, for example, SDN, and let's maybe even disable everything but the SDN for a while here, and we can then see the additional spots, which is positive and negative, and these are the positively associated voxels and the negative ones. Okay, so again, this is not at all significant. This is a model that we currently have on the stage that we can now explore further. One option I haven't shown so far is to mirror the data, right? So if you assume that your variable, for example, UPDRS improvement, is pretty much symmetric in, that not only the left hemisphere drives the whole effect or the right hemisphere, but you would assume it's, both drive it in the same way, then some people have used the strategy to mirror everything to one hemisphere. So for example, flip every VTA from the left side to the right side, and then you of course have double the n, so much more power on both sides. These maps should always look pretty symmetric. They are not 100% symmetric because we use an asymmetric template of the MNI space, and so the VTAs indeed get flipped non-linearly from left to right, so you might see very slight differences across the two sides, but as you can see, we're now looking from posterior. This looks pretty symmetric currently. Again, I have used these colors, from white to red and white to blue for positive and negative. And I'm showing both. Okay, so what we could now do is just, that we want to show only the significant voxels in an uncorrected fashion. And let's say we just want to see the positive voxels now. So this way, each voxel will be tested. We can refer to this as a masked univariate t-test, because we do the same test for every voxel. Since we do these multiple comparisons, we should correct for multiple comparisons, but this won't really work in this case, right? So that's why all this literature emerged, maybe starting from the Eisenstein 2014 paper, that rarely can we simply correct for multiple comparisons, and it even gets more complicated because, as mentioned in the beginning, not every voxel will be covered by the same amount of VTAs. Right, so probably you will nearly never find anything with with the correction strategies in here, right? But what you could do maybe to just look at the uncorrected significant clusters is to run this. And then you would see that the area that is now still there is much smaller, right? So as you can see here, it's really just this very small tiny bit within the subthalamic nucleus. For example, you could now export that as a nifty file, right? You could say, okay, this is my sweet spot. Again, this is not really significant now because we have done, we have performed a million of t-tests, and of course there will always be some positive values in there, right? So that the false positive rate is in this case at least 0.05. So we will definitely get alpha error accumulation. But maybe to recap, we have gone through quite a lot now. We have seen how this tool can be used just to explore the data, and that we can look at the data on different levels, and we refer to the manual for more details for that. But now all of the three tools that I'm showing you will do statistical testing by means of bootstrapping. So, for instance, we can use the leave one patient out strategy, which would now calculate this sweet spot based on all but the first patient, right? And then it would likely look pretty similar to that. Then it would take the VTA of the first patient, overlap it with that, and give it a score depending on how much score that VTA got, right? So if there's a lot of high T values, here you see the T values 406, if it would be a VTA that's directly in the center of this, then it would get a high score. Now, if it's something in the periphery, it would get a low score. Now we can repeat that, leaving out the second patient, and that would again lead to a new model that looks slightly different, and then we can predict that patient, right? So, and we could do the same using, for example, k-fold strategy, right? If we use five folds, that would mean these selected patients, so not all of them, but the 40 that we selected here, they would be split into random sets of 5. It's always the same random sets, and then the first set will be left out, then the model is calculated, and then the members, or like the entries of this first set, will be predicted. And that way, iteratively, we will get a prediction for each single patient, and we can now compare this prediction with the actual values, right? We could even say that we want to live visualize this. So during cross-validation, we want to see how much the model changes. I'll now do this without, on all the data, and we will just test this, and maybe we'll just take 3 folds. So, and we don't need to post correct for group, because the groups are not meaningful in our case. Now, if we run this, you will now see that each time in each iteration, a new model is being calculated and is being shown. But you can use this to look at, how much does the model change while doing cross-validation, right? Now we have the second set, now it looks slightly different. And so the degree of how much it will change could help you to understand, does this model seem to be robust? It's a bit similar to if we would say, we take a split half design, and that would be a 2-fold cross-validation. We train the model on the first half, and we also train it on the second half, and we just look at how stable that is, right? And remember, we are doing this currently only in the training and cross-validation set. So in terms of machine learning statistics, or the machine learning concept, sorry, we could also label this process as the model selection process, right? So again, what we did now is to divide these 40 patients into 3 sets, left the first set out, calculated the model, then predicted the first set. And we left the second set out, calculated the model based on the first and the third set, then predicted outcomes in the second set. And then we left the third set out, calculated the model on the first and the second set, and then predicted the patients in the third set. As you can see here, in fact, this label is wrong here. We've changed that. This is the basically the overlap, so the t-score of the VTA of the model, so in each VTA, and then this part is the empirical improvement. So these are the percent UPDS improvement values that you can see here. And you know, this might be a good first step, that we say, okay, this model seemed to be predictive, it's not highly predictive, and we can do model comparison within the training and cross-validation set, so slightly change the parameters and find a model that seems to be really robust in terms of cross-validation. You know, it's optimal if the model performs maybe in a leave one patient ORD design, but also in a k-fold design, maybe with different numbers of folds. So that way we are pretty certain this model seems robust within the data that we have. And finally, if at some point we would be happy with this, we can now, since we created, remember, the training and test subcohorts, we could now say we want to train the model on the training and cross-validation set and predict the test set. And that would be, you know, the very final step. Once we do this, we should not change the parameters anymore, because, you know, if not, we run the risk of overfitting our test cohort as well, right? And then this really becomes p-hacking, and you will always get a nice result, because you will, play with the data so much and massage the data so much to find something significant. So, you know, this again should, you know, once we press this button, in this case, we should not go back and change the parameters anymore. And if it fails, we should report that. So again, this is, okay, so yeah, we have a nice prediction, but it's not significant. In our case, the reason is that I would say that the test set I chose while doing this video was quite small, right? We have an N of only around 10 patients, so we would need a very high correlation to make that fit. So, you know, design the experiment better than I just did in this example, thinking about effect sizes and so on. But then once you divide your data set up into a training, cross-validation and test set, that will be helpful to then create a meaningful analysis. So this is as far as the tutorial for the Sweetspot Explorer. We will continue developing this tool, and we really would hope for your feedback, tips, suggestions, features that you miss, but also, you know, if you find problems with it or have questions about it, please best contact us in the Slack forum. And if you're a developer and want to contribute, we're always open for people that, you know, want to issue pull requests on GitHub. Now, we want to use the same analysis now to also look at which fiber tracts seem to be might be associated with clinical improvement. And to do that, we will add a fiber filtering analysis. As you can see, I already have a few in this project, but we'll now open up a new one, and you will find parts of this second tool very familiar. So the general idea of it is actually pretty similar. here you see the warning window or the hint window telling you a bit what I'm currently telling you, that, you know, these tools are powerful, but they could also be abused very easily. So the idea again is to really use the general principle of machine learning to divide your data on a training and cross-validation set, and then have a holdout set to test the data on. And yeah, so you can select do not show this dialog again and say makes sense, and then you should be all set. So if we compare the two tools, they look pretty similar, right? So you have again your analysis ID, and I can quickly show you that if you go into the lead group folder, you will have a fiber filtering one, which has the FibFilt extension. And the same thing applies if you drag that to a 3D viewer of Lead-DBS. That will open up the tool and show you everything, right? So that will work on every viewer, even of a single patient, or you can also easily open blank viewers by just typing MNI figure, right? So, and if you drag and drop one of these files onto such a figure, then you can look at it, right? So you don't always have to open up lead group, visualize all patients and open them, but you could also just drag and drop the analysis on here. Okay, so, and then in the beginning you will see the Fiber Filtering Explorer like this, where you cannot really do much, right? So everything is disabled. The only thing you can do is choose a connectome and to press calculate. And this already shows that, you know, the whole tool is set up only for use with normative connectomes. So this is essentially pretty different to the Sweetspot Explorer and also the Network Mapping Explorer, where this one, you know, the idea of it is really based upon using normative tract atlases or connectomes. Right, so we will choose this one for now. That's a beautiful atlas created by the lab of Cameron McIntyre, and Mikkel Pedersen is the first author, published in Neuron. And I will choose that also because it's quite small in size, so the calculation should be pretty quick. In the meantime, while this calculates, I will navigate to the Lead-DBS manual, and in here there under connectomics, and hopefully we will be able to update this. There is and extend this in the future even more, but under discriminative fiber tract analysis there is documentation about the two main concepts that we have implemented here. So the first one is based on correlations and E-fields, and the second one is basically built on VTAs and two-sample t-tests. Maybe to start, let's start with the VTA one, because most people are more familiar with the concept of binarized VTAs. You have to imagine a single fiber tract from the connectome that is put into MNI space, and we then have the small, then we have the VTAs of the whole group of the patients, right? So this is a group level scene here. And we only do this for one tract, but then we would repeat the same thing for every single fiber tract in the connectome. What we do is to divide the group of VTAs into the ones that are connected to the tract, so that, you know, seem to modulate or like activate this tract based on this very crude model that we use, and the ones that are remote and do not contact the tract. Right, so if we would believe the VTA model and say everything in this area is activated, then this tract will be activated by these VTAs, but not by these VTAs. Now for this tract, only for this single tract, we do a two-sample t-test. We perform a two-sample t-test across the improvement values of the patients with the VTAs that were activated, that activated this tract, you know, the ones here, the connected set, and the unconnected set. And now we can have 2 or 3 scenarios. Either the ones that were connected did better in clinical improvement, significantly better, or the other way around, they could do worse, or there's just, no difference, right? So that way we will get a t-value, and we can color code based on the t-value. If it's a positive one, we give it a red color. If it's a negative one, a blue color. And if it's in between, it's just a white tract. So every tract in our connectome, by doing this repeatedly, all the time, for every single tract, every tract will get a color or a t-value. And then we can do further calculations on that. In the other strategy, which is the Spearman's correlations or generalized correlations strategy, we do something pretty similar. So we again have this tract, but now we have E fields instead of VTAs. So these are not binary, they are not 1 or 0, but they are the electric field estimates, that have a high value in the center where the electrode is, and then the electric field magnitude vector fades out pretty quickly. So we can now, for each patient, in this tract, we have the tract is represented by sample points, and for each point of them, we will get a strong value for the VTAs or the E fields, that were close to this point, and the ones that are far away. Right. So we will get something like a value for each tract at each sample point. And then we could say, okay, we take the average of these values now, and crucially for this point, for example, even the E field that is really remote will still have a value, because the E field decays quickly, but it still has a small value here, right? So or at least most of the E fields will contribute to this and create some sort of value in here. And biologically, there will be no activation from here to here, of course, but there will be a value in the data set. What we could do now, we take the average of that, or we take the sum, or we take the peak only. So we take the peak activation, and we could now correlate this E field magnitude sum or average with the % clinical improvement. And if we have a tract that has a positive correlation, that is, maybe one that, let's assume the sweet spot is here, and this tract goes through the sweet spot, and then the ones that are far away from it, they will have a low impact on the tract, but also have a poor clinical improvement. But the ones with a high impact that are close to the spot, they will have a high clinical improvement and high impact on the tract. Then this tract will again get a very positive value, right? If we repeat it for a different tract, it might be the other way around, right? The correlation could be negative, that the ones that are as close to this tract or have the strongest impact on this tract perform the worst, are the poor improvers. Then this tract would get a blue color or negative R value, and again, if it's indifferent and not predictive at all, then it's a 0 value and white color. So the idea here is really how much can the tract discriminate between the poor responders and top responders. If it's predominantly modulated by top responders, then it gets a positive value. If it's predominantly modulated by the poor responders, then it gets a negative value, right? Okay, so this has been calculated now, and we can already see the hyperdirect pathway from this atlas, right? So we basically see that now we only have the positive fibers that have been modulated. Let's use a red color here again, just to synchronize the two analyses that we have. And you can also see the auto refresh in this tool is currently on, right? So we will, every change we make, we see directly. Similarly to before, we can also click on the show negative fibers. So we will also get, in this case, this is the dentatoroubro-thalamic tract of the left hemisphere, and probably nonsensical. We could also look at mirror the VTAs again to do the same as we did before, right? So this will, since we did it here, we'll do it here as well, and we assume that the effects of stimulation in PD would be more or less the same. But let's go through the tool step by step again. So as you can see, and as we've discussed in theory, there are two options. One is t-tests, one is correlations and E-fields. The results will of course slightly differ. In the correlations option, you can use different models, sum, mean or peak. And again, the improvement variable will be the one from our lead group analysis. And you can say which correlation you want to use. Spearman correlation is the original one we used in the first publication where we introduced this. That was Friedrich Ehrman's paper in Annals of Neurology 2019. And it makes sense, in my view, to use Spearman correlations because the association between E-field magnitude strength and improvements does not necessarily need to be a linear one, right? So Spearman's rank correlations will use the ranks, so that might be the best idea. But there are also different, more robust correlation options here. Okay, so now what are these two sliders? Now it gets complicated. So the first one is only active in the correlations E-fields mode. And it states that a tract will be considered connected if, in this case, the peak, right, E-field magnitude they traverse is above 0.2 volts per meter, right? So only if a tract goes through the peak of the E-field at least 0.2 volts per meter, then it is considered connected. And then connected tracts, that is a bit similar to the one slider we had here in the Sweetspot Explorer. We want to assure that the tracts are connected to at least a specific number of E-fields. This makes even more sense in the VTA mode. Here this slider doesn't apply at all because we have binary setups, but we want to, we compare, so remember we compare t-tests, so we do 2 sample t-tests, and if we would compare from our whole group 50 patients versus only 1 patient, then we cannot really do statistics on that, right? So here we have to assure that the tract are at least connected to something like 20% and not more than 80% of the VTAs, so that it divides the group of VTAs into 2 groups that are at least of some size, right? So something like this would probably not make sense, because then we would compare also tracts that divide the group into a very unhomogeneous sizes. But we also don't want it to make it 50, because then only the tracts that would divide it exactly in the middle, right, the tracts that are only connected to exactly half of the patients and not connected to the other half, only those would be considered. So this is, a limitation maybe of the VTA approach, that we have to divide the group into these values. If we use correlations, we could even say, just take everything. We want to take E-fields that tracts that are connected to no VTA at all, so no E-field at all, or all of the E-fields, we don't care. Because remember, in this case, we will always get a value for all of the E-fields, right? So we will always, even if the E-field magnitude sum can be really low and really high, we don't have the threshold in theory at all. Might still make sense to threshold, right? To say that we want to at least we want the tract that we consider to be at least connected to one of the VTAs very strongly, but it's not definitely necessary. So a good setting could be that we say, we want the tract to be at least connected to only one E field, a very small percentage of E fields in a very high fashion. So it should at least traverse through the center of at least one E field. Right? That could be something that, that could be a good setting, maybe. But again, these are the settings where we also don't really know. There are biophysical models that could be used, or literature data where you could look at, we assume a certain type of axon and we believe it's an all or nothing thing. We want to use E fields, but they need to be connected to that degree, and so on and so forth. So this is really the job of you as a scientist to decide what to set here. Now we can again clean the variable from covariates. In this case, it would even create put them into the model, so it's slightly different as in here with the covariates. And if we had more variables here, we could we would see these here, and we could clean the model from covariates. In terms of correlations, it will do basically partial correlations instead of correlations, cleaning the variables from these, and then in terms of, if you choose t-tests, it will perform linear mixed effects models, which are take a lot of time to calculate. So if we have understood these sliders, the right side is much more straightforward. So this part again does something very similar as here, but it does it in a fiber-centric way, because here we do mass univariate tests on a fiber by fiber basis. So the same applies. Correcting for multiple comparisons probably won't work if you don't have a very strong effect size. But what you could do is to say you want to consider significant fibers only the ones that are very strong. In this case that we're currently using, we use a Spearman correlation, so we get an R value for each fiber. We can see the R values here. So the maximum correlation of the maximum fiber is 0.39. The maximum negative one is negative to 0.29, and we will get a p-value for all of them. And now we are filtering the tracts that are below an alpha level of 0.05 in an uncorrected way. Again, correcting for Bonferroni will just not show you anything, right? Again, correcting for Bonferroni usually won't show you anything. Correcting for false discovery rate, in this case, even shows something. So, these fiber tracts would now be significant in themselves, which is nice. Okay, so now we have understood this. The other sliders here are pretty straightforward. So what we see is that there were 2,514 fiber tracts that had a positive R value, 444 with a negative one. From these, we're currently showing around 20%, which amounts to 244 of these. And on the left side, it's that amount, and on the right, it's that amount. So this is only, how much of these to show. If we would, slide this to the left, we would only show the 9 top tracts, and in this case, only the 7. And if we would slide it more, to the right, then we would show much more tracts. Here, if we have a setting where we want to show a lot of tracts, we want to maybe use them statistically, it makes sense to, again, deselect the auto refresh. Right now, if we change the slider, it doesn't refresh. Only if we click refresh view, then it will refresh, right? Okay, so then once we have something where we think, this has been now validated and so on, we can export this as an atlas. And we are always happy about novel atlases for Lead-DBS, or you can just send these atlases to colleagues or store them as a reference for your own lab. So, these results can then be exported in a similar way as we can export Sweetspots here as an atlas. But now what we want to do usually is to cross-validate data. We would usually do the same thing as we did here, right? So we would create a sub-cohort only on the training and cross-validation set. We would then do cross-validation here, and once we have a good model, we could then apply that to the test set to make the final test. But for the sake of brevity, I will now do cross-validation on the whole data set. You have the same options. Leave one patient out, for example. You could say we only consider the positive fibers, and we want to now show those exactly, and maybe some more fiber tracts. And you might want to use that as a cross-validation strategy. And again, you can click on the live visualize. As you can see, this is much faster than the Sweetspot Explorer to visualize. So, even a leave one patient out could be nice to visualize. As you can see here, MATLAB will now iterate through these sets, leaving out the first patient, the second patient, third patient, and so on. And each time you see how much the model changes. Optimally, you would want the model not to change as much, right? Because you leave out one patient, you don't want the model to change much. So this is a strategy during the model selection step in the beginning, in your training and cross-validation set, to look at how which set of parameters is giving me robust results. And in this case, it changed quite a bit. So again, also the cross-validation didn't yield significant effects. Right? So we have the empirical clinical outcomes, and then we have the predictions in terms of the fiber scores. So these values here would mean, we leave one VTA out, we calculate the model, and then we put the VTA on here, and we get the sum of t values, or in this case it's E field, so it's a weighted sum even, and we then have the empirical data here, right? So each time we leave out one E field, we calculate the set of fibers, so the model of optimal fibers, and then we use the left out, or we put the left out E field on there and validate it. And in this case, you also have to decide somehow what to base the prediction on, right? So the mean of scores would be that you would take from all parts of the E field the average of it, but the weighted average in terms of an E field, and the sum would be just how much of positive tracts are being modulated. So a bigger E field will always get a bigger score here, and then the peak would just be the peak. How much will the peak E field modulate, and so on. And then these are even more complicated. That I can is basically the profile, so the spatial correlation across the E field shape and the landscape of the model shape. And this shows, that again, the way of how to base how to do predictions can be done in various ways. There's probably not one single optimal strategy for this. But okay, so let's assume we find something that is a good set of fiber tracts. Now we have a sweet spot, and we have the optimal tracts associated with it. The third thing we can do is to add a network mapping analysis. To do that, we would click on the Add DBS Network Mapping Analysis. I will open a prepared one for now. When we open the DBS Network Mapping Explorer for the first time, it will also show us a hint stating a bit similarly what I just said before. You know, again, this is a powerful tool, but could easily be used in the wrong way. Maybe read the text, it makes sense. Now we have the third tool. Again, most of the things will look familiar. The idea here is, again, to use connectivity, and in this case we could use structural or functional connectivity. But instead of isolating tracts, we want to know, you know, which regions in the brain, maybe these regions up here, would be associated with good clinical improvement. So connectivity from the electrodes to which regions in the brain would be associated with good clinical improvement. And when you open it the first time, most things will be grayed out. Again, you have to choose a connectome and press calculate. I have used the structural connectome from the PPMI project, which is a Parkinson's disease progression marker initiative dataset of 85 patients. We pre-processed that in the paper by Siobhan Ewart in 2017. And we have also decided to work in a resolution of 2 millimeters. So if we press calculate, what happens under the hood is actually that the lead mapper tool is being run on these patients. Some of you might know this tool already. So this is basically where you can, you choose patients, select them, and select their stimulation parameters, and then run connectivity seeding from structural or functional seeds. Right. So this tool basically is opened up under the hood when I click calculate, and the result is directly stored in a network mapping folder. So to show you that as well, there's now in our lead group directory, we will see a new folder which is called network mapping, and again, same thing applies. This .NET map is just a mat file in disguise, and you could drag that to any Lead-DBS 3D viewer to open up this this tool and the results. Okay, so this DBS network mapping tool is built on the concepts that I've developed together with Mike Fox. I think the main paper is the one published in 2017 in Annals of Neurology, with different types of maps. So just to briefly go through it, we have of course the electrodes localized, we have the volumes of tissue activated or E fields. We can then use either a functional connectome to extract the time series of the specific, of the bold of the voxels of the bold signal in that VTA region, and we can also extract the time series of all other voxels, and we can basically just calculate functional connectivity seeding from the electrode to the rest of the brain. We will have positive connectivity values for the voxels that swing in sync, so basically are co-activated or are functionally connected, and then we have negative values for the anti-correlated regions. We can do the same using a normative connectome in structural form, which is represented by streamlines in Lead-DBS. So basically n times 3 matrices, each representing one of these fiber tracts. So we can select the tract the tracts that go through this region, and then put it onto the rest of the voxels of the brain. What we did back then is to have, we had two big cohorts, one from Berlin, one from Würzburg, and within the first one we did the classical model selection, tested different concepts by leaving sub-cohorts out within the Berlin dataset. and then we use the final model to predict outcomes in the Würzburg set. We tested different types of maps, and all of these are represented in this tool as well. You can see that here, right? R map, A map, C map would be the R map, the average map, the weighted average map, and the C map is the combined map. And we used, in the end, one model to predict outcomes across cohorts. So again, we have the improvement value that is from lead group, so we could have different values here. We can again clean that variable from other covariates. If we had more variables here, we could clean it from that. We could clean it from the cohort regressor and so on, simulation amplitude. Since we have selected correlations currently, we can again state which type of correlation we want to use. This is structural data, so in my view, Spearman correlation is a good call. If it's a functional connectome, then Pearson correlation is also fine. We can assume quasi-Gaussianity in that. Bend correlation and Spearman correlation are more robust, so you can also use those. As you can see, currently the auto refresh is not on, so and that doesn't make too much sense in this, I would say, because it takes quite a while to compute results. Here the same applies to before, right? We should again use a training cross-validation set. So for instance, if we had data from 2 cohorts, we could use the first cohort, or we could randomize. And again, we can also say, we want to mirror the VTAs. Same applies. I've shown this here. For now, I will just demonstrate it on all patients. And again, we will calculate correlation values from across like in each voxel in the brain. So we will also get a p-value. So we could again only consider significant voxels. Again, using uncorrected form, that would be the we wouldn't correct for multiple comparisons, so on. So I've explained that stuff before. This is showing negatives and positives, and then the question is how to visualize results. The default is to show results on a surface inside Lead-DBS. So the 3D view of Lead-DBS is called Elvis. You could also show it in Griswolden's surface, or you could show it as regions. And then if you show it on a surface, you can say you want to show it on a smooth surface. And let's assume we just want to show the left hemisphere because we have the tracts here, so maybe we want to combine things. Again, we use the red color to harmonize things across our analyses. And then if we have a nice result, again, we can export that as an IFTY file, right? So now I'll press refresh U and it's calculating the R map currently using Spearman correlation. So again, you can see that the same region roughly that was isolated by the fiber tracts is isolated also by the R map. So the regions in here, if we would use the same connectome, they should really correspond even better. So remember, here we used an atlas, here we used the connectome, but of course we could have used the PPMI here as well. So, but that way we would need to calculate it again. We can see that connectivity to this posterior regions was not associated with good clinical outcome, but the ones to the anterior regions and the motor regions was. So we see that on a surface now. If you would click on surface in surface and click on refresh view, it would calculate the R map, but then open up again the surface tool. Right, so here you can see the same representation we just saw inside Lead-DBS, but sometimes the surface viewer is just more beautiful, rendering it. And the third option is to show it as regions. So that will, instead of posting it to a surface, will calculate, or like will show the positive blobs of the nifty in 3D. This could be helpful sometimes if you're interested more also in the subcortex or in different, parts of the brain. Then you would really see which regions in the brain in a volumetric fashion are positively or negatively associated with good clinical outcomes. Right, so it's not as beautiful as you can see, but again, sometimes, especially in functional MRI or so, it can be really helpful because it could, for example, also identify, say, a region in the claustrum or putamen or so, right? So something that you would not see on the surface. So we'll go back to showing it as a surface. Okay, so now we have more or less concluded. Again, the same strategy applies here. So we could now use a leave one patient out strategy and use, for example, spatial correlations using Spearman for the similarity metric, and use, for example, a gray matter mask. We don't need to post correct for group, and we could again do the live visualization as before, and then we can click run and cross-validate our results. But to conclude, isn't that a nice view? Like that we have, one tool, the Sweetspot Explorer down here to determine or explore optimal stimulation sites. Then the Fiber Filtering Explorer to explore, optimal tracts or tracts associated with good clinical outcome. And then the DBS Network Mapping Explorer to look at, which regions in the brain would be associated with good clinical response. I hope you enjoy these tools. Don't be shy to ask in the Slack forum, contact us if you have questions, and if there are any issues with the tools, please also let us know. Thank you so much for watching, and have a good day.